Hi, this is the last day of derivatives notes. Next week we're just going to do integration, 2 days, and then we'll be done with the new material for the course. One day next week, I don't know yet if it's going to be Wednesday or Thursday, you're going to have an online test on derivatives and integration. And then from that point to the end of the school year, we're just going to be doing review, and the rest of your few tests that you're going to have to make up your fourth marking period average will be on review material. Okay, so I'm going to do derivatives day 4 notes out of order. So if you've printed your notes, you have 3 pages. So go to the 3rd page where it says second derivatives and higher, and it might be possible to differentiate repeatedly. So if you look at, again, we're going out of order. This is example number 3 on the 3rd page. And example number 3, the function f of x is equal to x cubed. So the first derivative, f prime of x, will be equal to 2x squared. That's just using your shortcut. The second derivative, f double prime of x, will be equal to 4x. The third derivative, which would be f triple prime of x, would just be equal to 4. And there would not be a fourth derivative of this function because the derivative of a constant is 0. So if you take a look at the notes underneath there, first derivative, what it's used for, second derivative, what it's used for, and there's a few different notations for second derivative. I'm just going to use f double prime of x. So let's run through real quickly example 4 and 5 for finding the second derivative. Example number 4, f of x is equal to x cubed plus 6x squared, x cubed plus 6x squared minus 9x. And you're trying to find the second derivative. So the first derivative, f prime of x, would be 3x squared minus 12x minus 9. The second derivative, you just do the derivative of this. F double prime of x is equal to 6x minus 12. So there's your second derivative. For example number 5, the second derivative, the first derivative is y is equal to the square root of x. Remember, you can rewrite this as x raised to the 1/2. That's review of the exponent chapter. That's still the original function. Your first derivative, y prime, is 1/2 x, subtract 1 from the exponent, raised to the negative 1/2. The second derivative, y double prime of x, negative 1/2 times a positive 1/2 is negative 1/4 x raised. When you subtract 1 from that, you get negative 3/2 for your exponent. That x would be written in the denominator with a positive exponent, so the second derivative is equal to negative 1 over 4. The x is going to come down here with a positive 3/2 exponent. The second derivative is equal to negative 1 times 4. That x raised to the 3/2 can be written under a radical sign. X goes here. It's going to be cubed, and we're going to take the square root. Rationalize the denominator. So it's going to be the square root of x cubed over the square root of x cubed. The second derivative is equal to negative radical x cubed divided by 4 x cubed, and then you have to include in your answer that x cannot equal 0. So that's first and second derivatives. Now, go back to the very beginning of these notes. And on the first page where it says derivatives day 4 and finding your local extrema for a function and where the function is increasing and decreasing, we've done this already. You had a question like this on your midterm exam. Step 1, find the first derivative. Step 2, do a sign chart on the first derivative. You need the extra row in your sign chart for the original function. If the first derivative is positive, your function's increasing. If the first derivative is negative, your function's decreasing. If your function is going up and then down, that critical value in your sign chart was a local max. If you're decreasing and then increasing, that x value in your sign chart is a local minimum. Take those x values, plug them back into the original function to come up with your corresponding y values. So we're going again back to the front of these notes. And we're going to look at example number 1 and find your intervals where the function is increasing and decreasing in all local extrema using the first derivative. So, example number 1, our function f of x is equal to 2x squared plus 6x minus 5. 2x squared plus 6x minus 5. Step 1, find the first derivative. F prime of x is equal to 4x plus 6. We have to do a sign chart on our first derivative. Now this is going to be a super easy sign chart, but it just runs you through the examples again. When you do a sign chart on the first derivative, you would have to factor the first derivative and come up with all your critical values. For this one, when you take that first derivative and set it equal to 0, x would be equal to negative 6 over 4. So x is equal to negative 3 halves. This sign chart is only going to have one critical value. So then when you set up your sign chart, we have one critical value of negative 3 halves. We only have one factor in our first derivative, 4x plus 6. Let me pick something less than negative 3 halves. Let me pick 0. This would be positive. If I something less than negative 3 halves would not be 0. It would be a negative number. Let's go with negative 10. If I plug in a negative 10 to my first derivative, this is going to be negative. If I plug in a 0 to the first derivative, this is going to be positive. So I don't need this extra row over here. Then my original function, f of x. If my first derivative is negative, my original function is decreasing. If my first derivative is positive, my original function is increasing. Because my function is increasing and decreasing, this negative 3 halves is the x value of a local min. So this has a local min at an x value of negative 3 halves. You have to take that x value of negative 3 halves, plug it back into the original function to come up with the corresponding y value. So if I evaluate f of negative 3 halves in the original function, 2 times negative 3 halves squared plus 6 times negative 3 halves minus 5. I'm going to say use your calculator. So f of negative 3 halves, the corresponding y value is negative 19 halves. Okay, so the local minimum of this function has an x value of negative 3 halves, a y value of negative 19 halves, and then you have to give me intervals where the function is increasing and decreasing. The function is increasing from an x value, it's wherever the first derivative is positive, so the function is increasing from negative 3 halves to positive infinity. The function is decreasing from negative infinity to negative 3 halves. And if I ask you for the local extrema, here's the coordinates of the minimum, but the local extrema would be a local minimum of negative 19 halves at an x value of negative 3 halves. Okay. Now, example number 2 on the back, as you can see, is quite long. I would highly recommend, if you have a printer, to print this out, and as I'm explaining it, look at it, stop the video, try to understand it. Okay, so algebraically, what I'm gonna do for this example, I'm not gonna do all the arithmetic, but I'm just gonna lay out like step by step what we're doing. So your original function, for example number 2, f of x is equal to negative 3x to the 4th plus 28x cubed minus 84x squared plus 96x. Right, so that's my original function. And I'm going to algebraically find where this function is increasing and decreasing in all local extrema. Step 1, take the first derivative. So f prime of x will be equal to negative 12x cubed. 3 times 28 is 84x squared. 2 times negative 84 is negative 168x plus 96. All right, there's your first derivative. Now we have to do a sign chart on the first derivative. This is where this question gets really crazy. And after we get through this, then I'm just going to talk you through the rest of it. Okay, so in order to do a sign chart, we have to factor this and come up with our critical values. Remember when you're factoring, you always have to factor out your GCF first. So our first derivative, in factored form, you would factor out the negative 12, and then you would be left with x cubed minus 7x squared plus 14x minus 8. Right, now, this polynomial function doesn't factor directly. You can't factor it by regrouping. So now I'm going to just talk you through something that we learned when we were doing synthetic division. So what you would need to do is you would just graph this. Let me back up. We should first of all identify our possible rational roots for x cubed minus 7x squared plus 14x minus 8. And that's your P over Q values. I know this is a lot of review. P is your lead coefficient. So P is equal to, no, P is not your lead coefficient. P is your constant. P is equal to 8. So the factors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Q is your lead coefficient. Q is 1, and the only factors 1 are plus or minus 1. So your possible rational roots from that cubic function, your P over Q values, because Q is just 1, would be all your P values. All right. Now you would graph the function. You would graph y equals x cubed minus 7x squared plus 14x minus 8. Look at your graph. From the graph, get a rational root. So when I graphed that cubic function and I looked at the graph, I got a rational root of x equals 2. Now I'm going to take this cubic function and I'm going to use synthetic division, and I'm going to reduce the cubic function until I can get it to a quadratic function. Then I'm going to have the factored form of my first derivative. So let's review synthetic division. I don't need any 0 placeholders. So there's a 1x cubed negative 7x squared 14x minus 8. I'm going to synthetically divide by my root of positive 2. Bring down the 1, multiply, you get a 2, add, you get a negative 5. 2 times negative 5 is a negative 10. Add, you get a 4. 2 times 4 is 8. Your remainder is 0. So the quotient would be x squared minus 5x plus 4. So now let me go back to our first derivative and the factored form of our first derivative. So our first derivative, f prime of x, had a GCF of negative 12. Because 2 was a root, x minus 2 would be a factor of our first derivative. And then the rest of the first derivative would be x squared minus 5x plus 4. we have to factor this one more time before we can come up with our critical values for our sign chart. So the first derivative is equal to a negative 12 times x minus 2, and the factored form of x squared minus 5x plus 4 is x minus 1, x minus 4. So now when you set up your sign chart, the critical values on your sign chart, you will have a critical value of x equals positive 2, x equals positive 1, x equals positive 4. Okay, so I'm going to erase this. Now I'm going to start with the sign chart, same question. I'll leave the original function up on the top. So I'm setting up my sign chart for the first derivative. In my first derivative, when I look at all the factors, I had one factor of negative 12. I have a factor of x minus 2. I have a factor of x minus 1. I have a factor of x minus 4. Then I'm going to have my sign for f prime of x for my first derivative. And remember, you need one extra row in your sign chart for the original function f of x. The critical values that we have for this sign chart are positive 1, positive 2, and positive 4. Because this is a negative 12, all of these boxes are going to be negative. So if I pick something less than 1, maybe 0, this is going to be negative, negative, negative. This would be a positive, times a negative would be a negative, times another negative. My first derivative here would be positive. That means that my original function is increasing. If I pick something between 1 and 2, like 1.5, this will be negative, positive, negative, positive times positive. My first derivative is negative. That means my original function is decreasing. If I pick something between 2 and 4, say a positive 3, 3 minus 2 is positive, 3 minus 1 is positive, 3 minus 4 is negative. So this is a negative, negative times another negative makes this positive. Our first derivative would be, or our original function would be increasing. And then something greater than 4, maybe a million, this would be positive, positive, positive. That means our first derivative is negative and our original function is decreasing. And I think I'm going to stop right there, but just talk you through the rest of it. So where is the function increasing? The function would be increasing from x values of negative infinity to positive 1, union, 2 to 4, not included. The function's decreasing between x values of 1 and 2, union, and then start again at 4 to positive infinity, not included. If my function is increasing here and decreasing here, this positive 1 is the x value of a maximum. So this function will have a maximum with an x value of positive 1. So the function is decreasing and then increasing, so this x value of positive 2 will be the x value of a minimum. So this function will have a minimum at an x value of positive 2. If my function is increasing and then decreasing, this x value of positive 4 will be a maximum. Now you have to find your y values. So what you would do at this point is you would take this positive 1, make sure you go back to the original function, plug it into the original function to come up with your corresponding y value, and that y value is 37. Then you would take this positive 2, plug it into the original function, and the corresponding y value is 32. Take positive 4, plug it into the original function, and the corresponding y value is 64. So these would be the coordinates of your max and your mins, but if you're asked for a local max, this function would have a local max of 37 at x equals 1. would have another local max of 64 at x equals 4, and it would have a local minimum of 32 at x equals 2. Okay, so that finishes up all your derivatives notes. 2 more days of new notes, and then we're done with the course. 2 days of integration, and integration is not hard. It's not hard at all. So guys, again, I hope you're doing well. I hope you have a great weekend, and I'll see you again on Monday.